This video will walk you through the example in Chapter 7 of the text. Specifically, we'll talk about the independent samples T, effect sizes, and confidence intervals. This video applies the 4 pillars of scientific reasoning to a research situation that is comparing 2 sample means that were collected from different groups of people. In other words, a situation in which you would use an independent samples t-test. Now you know 3 different t-tests. The first one is a single sample t, the related samples t, and the last one, the one we'll cover in this chapter, is the independent samples t. They have a similar logic, but you need to use them in slightly different situations. As you know, the single sample t, you compare a sample mean to usually a population mean, but it can really be any value of interest. So maybe a chance performance on a test might be 50%, and you could compare the mean of the sample to a 50% value. So in that case, it's not exactly a sample or a population mean, but it is some value that has some theoretical interest. So again, you have one sample mean and you're comparing it to some other value. In a related samples t-test, you have 2 sample means, and those 2 sample means come from the same group of people or 2 matched groups. And we talked about that in the last chapter. And now in this chapter, we'll talk about the independent t, and it's when you compare 2 sample means to each other, and those 2 sample means come from different groups, and those different groups are not matched in any way. The logic of the independent t-test is very similar to the logic of the previous t-tests. You have a mean difference that you observe in the sample, and you're comparing really the observed mean difference to what you would expect if the null hypothesis is true. And if the null hypothesis is true, you'd expect the mean difference between the 2 conditions to be 0. So really this term falls out of the equation, and it really just is the observed mean difference over the difference you would expect due to sampling error. And you can see that here. Here's the mean of group 1 minus the mean of group 2 divided by sampling error. If the mean difference is 0, or if the mean of the 2 groups are very similar to each other, essentially 0, the numerator of this t-test is going to be really small, and you're going to divide that by sampling error, and you're going to get a t-value that's close to 0. So again, this is a distribution of sample means, or a t-distribution. And again, if the numerator is going to be close to 0, you're going to get a t-value close to 0. Again, if the null is true, you're going to get something very close to this middle of the curve, a 0 for t. If you get something way out here in either tail, that's going to be strong evidence against the null hypothesis. You'll get a small p-value if you get something out here in these tails. The research question we're going to be using in this example is one on memory, and it's going to be asking the question, does providing a verbal label for a simple line drawing increase people's ability to recognize that drawing, say, 20 minutes later? The procedure was we had participants who were randomly assigned to one of 2 conditions. One condition saw 25 line drawings, one at a time, like this one. And another condition saw the same line drawings, but also was given this verbal label. After seeing these, 20 minutes later, they had a recognition test where they would see some figures that some drawings that they had seen previously and some that they had not, and they just had to say yes, no, this is one that I saw, this is one that I not saw. So it's a recognition test, again, 20 minutes later. Your scientific hypothesis, based on the previous literature, is that you would expect the verbal labels to increase recognition scores. The way human memory works, we tend to remember things better if we understand them, if they have some kind of meaning or some meaningful interpretation. And so providing these labels is meant to do that. So again, you have the scientific expectation that the group that is given the labels will remember more of the line drawings than the group that was not. Now, when it comes to designing your study, you have to make a few decisions. One of the decisions you have to make is whether or not you're going to do a one-tailed or two-tailed test. And as we've talked about a few times now, in most situations, a two-tailed test is going to be the more appropriate test. In this case, you expect that the group that's given the label is going to remember more. But if the opposite happened and the group that was not given the labels remembered more, that would be really interesting, and you would still report on it because it would be running counter to what a lot of previous research has indicated. So you would want to report that. You would want to figure out why that happened. So in this case, a two-tailed test seems like it would be more appropriate. You also want to make a decision about sample size. In this case, the previous research reported that they had found really a very large effect, a D of 1.5. Using the table in chapter 5, you know that if previous research suggests that you might find a large effect, that you can get by with a sample size as small as 25 people per condition to find that large effect. The study that we're going to do actually had 70 people in the study, 35 per condition, so you should be fine. This should be a sufficient sample size to have enough statistical power to detect a large effect. Pillar 1, of course, is hypothesis testing with a continuous p-value, and the first step is to choose the correct test statistic. And as we said previously, in this situation, you're comparing two sample means from different groups of people. So an independent sample t-test is the appropriate choice here. Specifically, we're comparing the mean number of line drawings that were recognized by the verbal label group versus the no verbal label group. The second step is to examine the statistical assumptions. Data independence is the idea that one person's responses are not influenced by a different person's responses. So in this case, we just would want to make sure that one person maybe isn't copying off another person or something. So in an independent samples design, you just want to have good procedural control to just control for the fact that each individual person's responses are independent of anybody else's. The second one is appropriate IV and DV measurement. In this case, the independent variable is identifying how the two conditions are different from each other. Well, one group is getting a verbal label and the other group is not. So those are our two levels of the independent variable. The independent variable is a condition or what information they are given. And one group is given the labels and one group is not. So that is two levels of the independent variable. The dependent variable is measured on an interval or ratio scale. In this case, it's specifically ratio because we're measuring how many out of 25 simple line drawings students or participants remember or recognize. And so the lowest score is 0, that you can't get a negative number, so that makes this a ratio scale. So this assumption is met. Normality, of course, deals with the central limit theorem. It is the assumption that the distribution of sample mean differences has a normal shape. And of course, that will happen if either of two conditions have been met. If the distribution of sample, or if the population of mean differences between these two conditions has a normal shape, then the distribution of sample means will have a normal shape. And that's what's going to be the case here. We have good reason to believe that the population would have a normal shape when it comes to mean differences. But another way of being fairly confident that you're going to have a distribution of sample means with the normal shape is if your sample size is sufficiently large. And in this case, we have 35 people per condition, which is generally going to be enough to make us pretty confident that the distribution of sample means will have a normal shape. So we are comfortable that we have satisfied the normality assumption in this situation. The last one is something called the homogeneity of variance assumption, which simply means that the two conditions in the population have similar variances or similar standard deviations. Now, we can assess this assumption in a number of ways. There is a formal test you can use if you're running it on a computer or computer software called the Levene's test. And what that's doing is it's just comparing the variability in the two conditions to see if they are very, very different or fairly similar. If you look at the Levene's test and you get a small p-value, then you should use the Welch's t-test, because the Welch's t-test does not have a homogeneity of variance assumption. So if you get a small p-value, that means that the two variances are fairly different. Now, what do I mean by small? Let's say 0.05 or less. If you get a p-value of 0.05 or less for the Levene's test, then you can use the Welch's, because again, the Welch's does not assume homogeneity of variance. If the p-value is not small, then you could go ahead and use the student t-test. This is the most common t-test that's used. Some people argue that we should just always use the Welch's test, because why make an assumption if you don't have to? So if you don't have to assume homogeneity of variance, then why assume it? Just use Welch where you don't have to assume it. Well, there's a good argument for that, but most researchers still use the student t, and there's a good argument for using that too. If you are trying to estimate a population, the student t estimates the variances and the sampling error differently, and arguably, if the variances are similar, pooling all of that data together gives you a better estimate for the population. So there's a good argument for using a student t when you can. Again, there's disagreement. There's not really a wrong answer. People argue about it in the literature. Just make sure you use one of the two and tell people what you're using. In this class, we're going to use the student t-test whenever we can. Now, sometimes you're doing it by hand and you don't know, you don't have a computer to run the Levene's test for you. So you might use this rule of thumb, which is generally accurate. If one of the two groups has a standard deviation that is 3 times the other, then you might have a violation of the homogeneity of variance assumption. Another thing to look at is if the two groups have equal sample sizes, you're less likely to violate this assumption. The third step is to identify the statistical null hypothesis. Again, as always, the null hypothesis is saying that there's no effect. So in this case, you would expect the mean difference between the verbal label group and the no label group, that mean difference in number of recall of simple line drawings, the number of simple line drawings that they recall would be 0. Symbolically, it would be reflected like this. So the verbal label group mean minus the no label group mean. If you subtract those, you're going to get 0 if the null is true. Now, if you get a mean difference of 0, that will produce a t value of 0. And that's reflected down here in this curve. Again, this is a distribution of sample means, or a t curve. And if the two means are very similar to each other, essentially the mean difference is 0, you're going to get a t value that's very close to 0. Again, it's peaked over 0. Again, this is assuming if the null hypothesis is true. If you get something way out in the tails, you're going to get a t value far from 0 on the negative end or far from 0 on the positive end. You're going to get a low p-value, which again will be compelling evidence that the null hypothesis is probably not true. Again, you expect to get something close to 0 if the null is true. It's possible to get something way out here, say a 2.5 or something. It's possible for that to happen if the null hypothesis is true. It will just have a very small p-value. is not highly likely, it's not probable to happen if the null hypothesis is true. And if you get something out here, you conclude, oh, it's not probable, it's not likely to happen if the null is true, so you conclude that the null probably is not true. The fourth step is to graph the data from each condition. And in this case, you can see that the group that was given the verbal label recalled more simple line drawings than the group that was not. And this is helpful just because now when you go down to the next few steps, you know which direction the effect is going. You know that the evidence looks like it's leaning towards your scientific hypothesis in this case, because you predicted that this group would have a higher mean performance when it comes to memory score. Of course, now you still need to go down and run the statistics and find if the p-value is compelling enough to argue that this difference is unlikely to be due to sampling error. So now we need to compute the t, the independent t, and determine its p-value. So here's the mean difference, and then you're dividing it by sampling error. The mean difference you would expect just due to sampling error is the denominator. This is the mean difference you have. And so when you crunch these numbers, here is the actual mean difference, and this is the mean difference we'd expect due to sampling error. So you're simply dividing sampling error into the mean difference, and now you find that the t is 2.1. That literally means that the observed mean difference is more than 2 times larger than what you would expect due to sampling error. That's going to be pretty compelling evidence. That converts to a p-value of 0.036, and you can see this in this curve. So the obtained t, this is a two-tailed t value, so we have to put it on both ends. Here's the obtained t, and then it's reciprocal on the other end. So basically, this is about 2% of the curve. This is about 2% of the curve, and when we add these two things together, we get this. There's some rounding error down here. So the two-tailed p-value is about 3–4% of the curve here is what this p-value means. We'll interpret this p-value a little bit more in the next slide. Again, we expect a t-value something close to 0 if the null is true. We clearly got something far from that. So this is probably going to be pretty compelling evidence. It is, because this is a p-value that's small enough to offer compelling evidence. But we'll interpret this more on the next slide. So here is our p-value, and that is literally the probability of getting a t-value of 2.135 or further from 0 on the positive end or the negative end if the null is true. So that outcome, or something more extreme, is pretty unlikely to happen. About 3 to 4% of the time when the null is true and there are no methodological flaws in the study. Therefore, this is pretty compelling evidence against the null hypothesis, and these data suggest that verbal labels do tend to improve memory recognition for simple line drawings. The next step is to assess the practical importance of the effect we observed. Is it large enough to have practical importance in the population, or is it unimportant because it's such a small effect? You have a number of options. You can use the mean difference, or you can use the standardized effect size. The mean difference is simply the mean of the group that got the verbal labels minus the mean of the group that didn't, and that gives us a mean difference of 1.286. That's just suggesting that the verbal group recognized that many more line drawings on average than the control group. Sometimes it's useful to convert this raw mean difference into a percentage. In a sense, you're kind of standardizing it again. But if you do that in this case, it comes out to be about 5% higher. that kind of helps you calibrate the mean difference to sort of decide whether that's important or not. Generally, on a test in a classroom, for example, if you're doing 5% better on that test, you're probably gonna think, oh yeah, that's practical, that's important. 5% improvement's a big improvement if you're talking about maybe an 80% to an 85, right? You're talking about a B minus to a B. So yeah, a 5% improvement in memory performance probably has practical importance. In most situations, you would think that it would. You can also go down to the standardized effect size here, which is the mean difference divided by the pooled standard deviation. And that gives us a Cohen's d of 0.5, which is a medium effect. And in most situations, a medium effect is going to have practical importance. Again, you would want to use one of these. It's probably not important to talk a lot about both. You might report both, but only discuss one. Whatever one you think is more meaningful in the situation you're in. This is perhaps more helpful to help people. The mean difference is probably more helpful to help people understand the specific study and its effects. But if you want to compare your results to another study's results, perhaps converting it to D would be better. If they converted theirs to a percentage as well, then that might be equally effective. So again, it just depends on the situation. You want to pick and choose the effect size that helps you describe your effect most accurately. The next pillar, of course, is population estimation with confidence intervals. And you have a couple of those as well. You can do the 95% confidence interval around the mean difference. In this case, the mean difference was 1.3 essentially. And so that is the point estimate. And then we add and subtract from that the margin of error to get the upper bound and the lower bound. Again, I'm not going to go over how you compute the margin of error. It's discovered or it's explained in the text, and I'm happy to go over it with you individually if you want. But again, in this class, we're going to focus more on interpreting these things than computing them. So in this case, we have an upper bound and a lower bound here, and this suggests that the difference in memory score in the population could be as high as basically 2.5, which is almost 10% higher for the people who get verbal labels, or it could be as low as essentially 0. Very modest effect. When you have, look, we have an upper bound that says this is a very large effect, and we have a lower bound that's saying this is a very small effect, or it could be. Again, these upper bound and lower bound bracket the plausible values for the population parameter. If our sample represented the population well, we would expect the population to be about 1.3 mean difference and about a 5% benefit for the verbal labels. But because of sampling error, we might be off by quite a bit, and the effect could be quite a bit larger than we observed, or it could be quite a bit smaller than we observed. So you just want to be, when you have this wide of a confidence interval, you want to be a little tentative. You want to say, well, it could be a bit higher, it could be a bit lower when you conclude your, write up your conclusion. When you have this wide of a confidence interval, it might be worth doing the study again if you really want a more precise estimate, because a larger sample would give you a more precise estimate. You can also get a 95% confidence interval around D. This is done by computer. We don't really do this by hand. In this case, the upper bound suggests that the effect might be large. Again, 0.8 is considered large, so this is nearly 1, so this is very large. And a 0.2 is considered small, so this is quite a bit smaller than 0.2. So again, we're getting similar indication as we did up here with the mean difference. The effect in the population could be very large or it could be very small, suggesting that if we want a more precise estimate, we probably want to do a study with a bigger sample size. The final pillar, of course, is considering the methodology and the scientific literature to provide a scientific context of these results. The methodology used in this study was sound. We randomly assigned participants to conditions, which is a good thing to help control for something called initial equivalence. So that's good. Make sure the two groups are equal before we start. And the participants were run individually so that one person couldn't necessarily copy off another person. These are good, sound procedural controls. The literature suggested results that were very similar to the results that we found. They also report that verbal labels benefit memory for line drawings. So you're going to want to mention that in your scientific conclusion, and you're also going to want to provide an interpretation of the results. Again, you're the expert, and the reader's going to want to know what you think of the data. Here's an example of a well-supported scientific conclusion. As with all of the scientific conclusions we presented in this book so far, you want to do 6 things. What are you comparing and how did you compare it? You want to report the sample statistics, interpret the p-value, the effect size, the confidence interval, and also comment on the methodology and scientific literature to the extent that you're able. An independent sample t-test compared the memory recognition scores of those who got verbal descriptions, then I'm saying what their mean and standard deviation were, and those who did not get those verbal descriptions. So that's what I compared and how. Then all of these numbers are giving me the sample statistics in APA format. Here's the mean and standard deviation of the verbal label group. Here's the mean and standard deviation of the group that did not get them, the control group. We had 70 people in the study, which means our degrees of freedom was at n-2 in this case for an independent t, so that's 68. Here's our obtained t-value. Here's our p-value. Here's a 95% CI for the mean difference. And here's the 95% CI for the d. Right there. And then there's the confidence interval for it. Now I need to interpret the p-value. The evidence suggests that providing verbal labels with line drawings improves subsequent memory performance more than would be expected by sampling error. That's because this p-value, again, is compelling. In this study, the improvement was moderate in size, approximately 5%. An improvement of this size likely has practical importance in that a 5% improvement would be noteworthy in any classroom. That's an interpretation of the effect size. Notice I chose to talk about the 5% improvement. I still reported the D up here as an effect size, but now when I'm interpreting it, I'm choosing to talk about the 5% improvement. Again, you could choose to talk about the D. I just chose to talk about this one because I think everybody kind of understands what 5% higher on a test means, so I chose to talk about that one. Next, I want to talk about the confidence interval. The wide range of plausible values for the population indicates that this study provides only a rough estimate of the effect. Performing a study with a larger sample size would provide a more precise estimate. Again, I just want to comment a little bit on each of these factors. So the confidence interval here, I'm really look at how wide these are, and I'm just drawing the reader's attention to those. Again, we're confident the effect is happening because that's what this p-value tells us. It's probably going to happen in the population, but we just don't know. We're not very confident in the size of this effect as it occurs in the population. It could be pretty small or it could be really large. Probably it's somewhere in the middle. Again, if our sample is fairly representative, your best guess is that the population parameter is somewhere in the middle of the confidence intervals. But if you got a bad sample, it could be on either the low end or the high end. So it's important to recognize that possibility when you write your scientific conclusion. Finally, you want to comment on the methodology and scientific literature. In this case, I did it in a pretty sparse way. Rather than commenting specifically on the strengths of the study with random assignment and good procedural control, I just said there's no methodological flaws in the study. which is pretty minimal but acceptable. Then I also talk about the scientific literature. These results are consistent with those reported in by other researchers, and then I would cite them, of course. So this is a fairly brief conclusion, but it does have all of the components that we're looking for. So this would be a solid scientific conclusion. If you're interested in learning more about statistics, visit us at learnstats.com.